Welcome on to day 8 of this online course Physics with Scilab. Today we will see the solving first and second order differential equations ODE solver. In Scilab, the explicit ordinary differential equations defined by dy by dt is equal to f of ty with the initial conditions y of t0 equal to y0 can be solved using the built-in function ODE. The simplest call of ODE is y equal to function ODE with the four arguments. First is y0, that is the initial condition or initial value of y. T0 is the initial time. T is the times at which the solution y is to be computed. F is the function defines the right hand side of the first order differential equation. This function has a specific header. Now let's see an example of solving the first order differential equation. So in this example, we have to evaluate the value of y at x is equal to 1.4, where the first order differential equation is dy by dx is equal to x square into 1 plus y, and the initial condition is y of 1 is equal to 1. That is, y0 is equal to 1 at t0 is equal to 1. So we will take the ODE function with the four arguments. So this is the syntax for defining the function. The initial conditions y0 is 1, x0 is 1, x is 1.4, and the function is equal to x square into 1 plus y, which is the right hand side of the first order differential equation. Now let's solve this differential equation in Scilab. This is the code that I have written in Scilab to solve this first order differential equation. So first command CLC to clear the console. Then I have defined the function dy is equal to f of xy, where dy is equal to x square into 1 plus y, which is the right hand side of the given differential equation. Then end function. Now x is the vector for the values of x for which I want to determine the values of y. Then the solution equal to the function ODE with the four arguments 1, 1, x and f, where 1 is the value of y0, second one is the value of x0. So this 1, 1 shows the initial condition. Then the x, it is the variable for which we want to solve for y. So this is a vector of the values from 1 to 2 with the step size of zero point 0.1, and f is the defined function which is the right hand side of the given first order differential equation. Then the command display solve, which is to display the solution of the differential equation on the console, and the plot 2D function, which is for plotting the solution for these values of x. So now I will save and execute this program. Values for y for different values of x that we have given and this is the plot of x and y. Now we will try one more example. So here the differential equation is dy by dx is equal to x square plus y square divided by 2 with the initial condition y of 0 is equal to 1. Then we call the function ODE to solve the first order differential equation. Y0 and x0 are the initial values, x is the differentiation variable, and f is the right hand side of the first order differential equation. So this is the syntax written to define the function. So now we will move on to a console. So this is code written to solve the first order differential equation. Again started with CLC, define the function dy is equal to f of xy, where dy is equal to x square plus y square divided by 2, that is the right hand side of our given first order differential equation, and end function. So this is the vector for the x, which are the values of x to be supplied to the ODE function for getting the values of the solution or y. Then the command display the solution, and again the output we will get in the form of a graph with this command plot 2D, which plot the solution against the value of x. So I will save and execute this program. So these are the values of the solution or y at different values of x. Again, we can see the plot of the solution or y with the values of x. So this is how one can solve the first order differential equation using ODE solver in Scilab. Now solving second order differential equations. So to solve the second order differential equations, we have to convert the second order differential equation into two first order linear differential equations. So let's see the example. Solve the second order differential equation to get y and y prime with y equal to zero point 0.5 and dy by dx is equal to zero point 0.1 when x is equal to 0. So y prime is nothing but dy by dx. So the differential equation is d2y by dx square plus 2x dy by dx plus y equal to 0. So first step is to rewrite this equation to d2y by dx square value. So it is equal to minus 2x into dy by dx minus y. Then next step is to write the another symbols for y and dy by dx, that in this example I have taken the t1 and t2. So I put y is equal to t1. So the initial condition for t1 or y is zero point 0.5 when x is equal to 1. Similarly, dy by dx or y prime I have put equal to t2. So the y prime as the initial condition or initial value is zero point 0.1. So now from these three equations we can have t1 prime equal to t2 and t2 prime equal to minus 2x t2 minus t1. These two equation will give you the first order differential equation, because here y is equal to t1, therefore dy by dx is equal to t1 prime, and it is nothing but t2. From the second differential equation, if we take a t2 prime, that is d2y by dx square is nothing but, from the first step, minus 2x into dy by dx, that is t2, minus y, that is t1. So in this way we can get the two first order linear differential equations. Now let's move on to the Scilab to solve these two differential equations. To solve this second order differential equations, I have already written here the code. So CLC and CLF are the commands for clearing the console and clearing the figure on the graphics window respectively. Then the function dy is equal to f of xt I have taken, where x is the first variable of the function f, which is the variable of the given differential equation, and the second variable I have taken t, which is I have used for the y and y prime. Then the first equation dy of 1 is the first order differential equation, so it is equal to t2. So here I have written t of 2. Then second dy of 2 is a second first order differential equation, so dy of 2 is equal to minus 2 into x into t of 2 minus t of 1, then end function. So the initial conditions are, at t0 equal to 0, y0 is zero point 0.5 and y0 prime is zero point 0.1. So here the vector for t has the values from 0 to 0.5 with the step size of zero point 0.1. Then the solution is equal to function ODE in the argument y0 semicolon y0 prime. So these are the values for the initial values for the y0 and y0 prime. Then t0 is the initial time, which is 0 in this case. Then t is the same vector for which we want to get the values of y and y prime, and f are the two functions for getting the value of y and y prime. Then the command is for display the solution, and next is to plot the solution against the values of t. So in the argument of plot 2D function, I have written t comma solution 1 comma double colon. So here I want to plot only the values of y against t, then comma 5, that is style. So this will give me the color of the graph red. So now I will save and execute this. So these are the values. So in the row of zero point 0.5, the values are of y, and in the row of zero point 0.1, there are the values for y prime or dy by dx. And similarly, on the graphics window, this is the plot for y, or solution of the second order differential equation with the t, or variable x. Let's see one more example. Obtain the solution of the following second order differential equation with the initial condition y of 0 is equal to 1 and y dash of 0 is equal to 1 by 2. So the initial condition is at x is equal to 0, y is 1 and y prime is 1 by 2. So differential equation is d2y by dx square minus x cube into dy by dx minus x cube y equal to 0. So step 1 is to solve or rewrite this equation for d2y by dx square. Then step 2, use the symbols t1 and t2 for y and dy by dx. So if we put y is equal to t1, then dy by dx will be t prime, that is equal to t2, and similarly d2y by dx square is equal to t2 prime equal to x cube into dy by dx, that is t2, plus x cube into y, that is t1. So in this way we can convert this second order differential equation into two first order linear differential equations. Now let's go on to the console. We have the two equations, that is t1 prime is equal to t2. So this is the same. So for which I have written dy of 1 is equal to t of 2. Then for the second first order differential equation, that is t2 prime x cube t2 plus x cube t1. So here there is dy of 2. So only I have to change the right hand side. So I want x cube into t2 plus x cube into t1. So this changes I will make here, x cube, that is x raised to power 3 into t2 plus x cube into t1. So x to the power 3 into t1. So I will put it into parenthesis to avoid the confusion. Again, so for this case, we have the initial condition t0 equal to 0, y0 is 1 and y0 prime is 1 by 2. So I take it is 0.5. I will use the values for the vector t from 0 to 1 with the step size of zero point 0.1, and the argument of this ODE function I will keep same because I have used the same variable as in the earlier example. Then display the solution and then plot 2D function to plot the solution against the variable, and here instead of 5 I will take 4. That will give me a plot in another color. So save and execute. So these are the solutions for y, and this is for y prime. And let's see the plot. So this is the plot for the solution against the variable x. So in this way we can solve any first order or second order differential equations with this ODE solver. That's all for today. Tomorrow we will see the examples of the second order differential equations from physics.